let's jump right into this. When you think of an IT workspace or a computer lab, you probably just picture a quiet room, right? Humming servers, glowing screens, pretty low-key. But the reality? It is actually a high-stakes environment where hardware literally lives or dies by your actions. The safety rules we follow aren't just polite suggestions. They are the literal difference between a smoothly running network and an incredibly expensive disaster. So, in this explainer, we're going to dive into the IT survival guide and explore exactly how to keep both you and your tech safe. To really understand the stakes, we need to look at the shocking contrast in durability between us and our machines. Think about it like this. A human being usually doesn't even feel an electrostatic shock until it hits over 3,000 volts. 3,000. But the delicate microcircuitry sitting inside a computer, that can be completely, and I mean permanently, destroyed by less than 100 volts. That is a massive difference. We are basically walking lightning storms to these delicate components, which perfectly illustrates exactly why these safety procedures are absolutely critical. All right, let's get into Section 1, Essential Lab Safety Rules. We need to establish our baseline. You really can't talk workplace safety without bringing up OSHA, the Occupational Safety and Health Administration. They are the federal agency charged with enforcing safety and health legislation, so they're basically the ultimate authority here. They set the core mandates for a safe environment. That means they're the ones requiring IT shops to provide properly maintained tools, keep rigorous records of any accident reports, and display those OSHA compliance posters you see on the wall. It all starts with compliance from the top down. So how do OSHA's broad mandates translate to the absolute most crucial rules for technicians working right at the bench? Well, first up, absolutely no food or drinks in the work area. Literally, one spilled coffee can ruin thousands of dollars of equipment. Second, always remove all jewelry and watches before you begin working. These are conductive materials, so they can snag on components or conduct electricity right into your skin. Third, never use magnetic screwdrivers near sensitive components, because those magnetic fields can actually wipe data or damage circuits. And finally, here's a great pro tip. Always cover the sharp edges of an open computer case with tape. It stops you from slicing your hands open and prevents wires from getting damaged during installation. Okay, I need you to burn this next rule into your memory. Amps kill. Never, ever open or work on a monitor or power supply. This is where we drop the fun and get very serious. Some components inside a computer are simply off limits to general technicians. Why? Because they retain lethal amounts of electrical current long after they've been unplugged. You can totally replace a power supply entirely, but never open the casing of one to try and fix the insides. Just don't do it. Moving on to Section 2, Managing Hazards and Emergencies. Let's talk about what happens when things actually go wrong. Behold your primary tool for fighting lab fires, the classic fire extinguisher. But here's the crucial point. Not all fire extinguishers are created equal. Most general use extinguishers that you'll see hanging around are rated ABC. But what do those letters actually mean, and why does it matter so much in an IT environment? Let's break that down. So here is how the different classes shake out. Class A handles ordinary combustibles, paper or plastic. Class B takes out flammable liquids like solvents. Class D is for combustible metals. But as an IT professional, your eyes need to immediately go to Class C. Class C is specifically rated for electrical equipment, appliances, switches, power tools, and obviously computers. If a server rack catches fire, using a Class C rated extinguisher means the extinguishing agent won't conduct electricity back up the hose and shock you. Always verify your lab has a Class C capable extinguisher. Now, fires aren't the only hazard. What about chemical spills? Say a massive toner explosion from an industrial printer, or maybe a specialized cleaning solvent spill. For that, we turn to the MSDS, the Materials Safety Data Sheet. Think of this as your ultimate survival manual for chemical encounters. It provides the exact procedures for safely handling a substance. It lays out the toxicity, immediate health effects, and most importantly, the specific steps for cleaning up a spill without endangering yourself or the environment. Section 3, Enabling Tech for Everyone. Let's briefly shift our focus from physical danger to computer accessibility. Ensuring everyone can safely and effectively use the lab is a huge part of IT. Modern operating systems are packed with incredible built-in features called assistive technology to overcome specific impairments. For dexterity impairments, we can enable sticky keys, which lets users press complex keyboard shortcuts one key at a time instead of mashing them all at once. For visual impairments, we're talking large fonts, high DPI displays, screen magnifiers, or even braille displays. And for hearing impairments, we can pair system sounds with high-contrast visual notifications or closed captions. Knowing how to quickly deploy these tools is just a basic requirement for a good IT pro. All right, Section 4, the threat of ESD. This right here is your primary adversary when handling hardware. So let's define it. Electro-Static Discharge, or ESD, is the rapid movement of electrons resulting from a charge buildup seeking a lower charged outlet. Let me put that in plain terms. Our bodies are constantly generating and storing static electricity. When we touch a piece of conductive material, say the gold pins on a stick of RAM, those stored electrons aggressively jump from our body right into the component. It happens in a tiny fraction of a second. You won't even feel it, but that microchip, it's completely fried. So how exactly do we fight an invisible enemy? This is your primary defense, the grounding wrist strap. You strap the fabric band tightly to your bare wrist, and then you clip the metal end to the unpainted metal chassis of the computer case you're working on. What this does is equalize the electrical charge between your body and the computer. With the charge equalized, the static electricity literally has nowhere to jump to. You're safely tethered. But creating a truly safe environment requires a full multi-step approach. Step 1 is always the wristband, for sure. Step 2 is working on specialized ESD tables or mats that safely dissipate charges. Step 4 ensures we transport vulnerable parts inside those shiny, shielded anti-static bags. But actually, look at Step 3. This is super fascinating. Keep room humidity between 40 and 60%. Static electricity builds up much, much faster in dry air. By simply using a humidifier to maintain that specific moisture range, you naturally blanket the entire room in a layer of protection that actively reduces static buildup. How cool is that? And I definitely want to highlight this one specific rule, because it is incredibly easy to forget when you're rushing to fix a problem. Just allow 15 seconds to pass before touching any sensitive electronic components with bare hands after you power down or move to the station. Giving the system and yourself a brief 15-second pause allows any lingering, uneven surface charges a moment to dissipate. It's a remarkably simple, completely free pro survival tip. Okay, bringing it home with Section 5, power, protection, and backup. Time to defend against unstable power. We tend to assume power from the wall is perfectly clean. It is rarely clean. The invisible enemies attacking from the external power grid include line noise, spikes, surges, brownouts, and blackouts. A spike is a very brief, massive increase in voltage, while a surge is a longer-lasting increase. A brownout is a highly dangerous drop in voltage, and a blackout is, well, a total loss of power. Any single one of these fluctuations can instantly corrupt data or cause catastrophic reliability issues for a computer. To combat grid threats, we basically rely on two main pieces of hardware. First, we have the surge suppressor. Think of this as your shield against too much power. It physically absorbs incoming spikes and surges before they hit your computer, and high-end models even smooth out erratic line noise. On the other hand, we have the UPS, or uninterruptible power supply. Think of this as your defense against too little power. When the wall power suddenly drops in a brownout or blackout, the internal battery of the UPS instantly kicks in, giving you precious time to save your work and safely shut the machine down. But if you dive a little deeper, you'll find there are two distinct architectures for UPS systems. A standby UPS is the most common one. It normally operates directly from the AC wall power, and when it detects a drop, a physical switch flips over to the internal battery. It works, but there's a tiny millisecond delay during that switch. An inline UPS, however, is brilliant. It continuously operates from its DC battery backup side, actively converting the wall AC power just to keep the battery charged. Because the computer is always running off the battery anyway, if the wall power dies, there is absolutely zero switchover time. Perfectly seamless power. Which brings us to our final, incredibly critical hardware-saving warning. Never, ever plug a laser printer or a monitor into a conventional UPS. See, when a laser printer warms up its fuser, it draws a massive, sudden spike of electrical current. If it's plugged into the battery backup side of a UPS, that huge power draw will instantly overload and very likely destroy the internal circuitry of the UPS itself. Save your backup battery outlets strictly for the computer tower. And that brings us to the end of our explainer. We've covered the shocking voltage hazards, the strict OSHA rules, fighting the invisible threat of ESD, and stabilizing power. But I want to leave you with a provocative thought. You now know how to physically survive the lab, but how effectively can you communicate these high stakes to the end customer? See, troubleshooting is as much about professional communication and managing human expectations as it is about knowing how to swap a motherboard. So, as you master the hardware, ask yourself, are you ready to master the human side of IT? Keep learning, stay curious, and until next time, stay safe out there in the lab.